Last time I didn't prove the main theory, right? That if we have a finite extension of degree n, then if we define the norm as the p-adic norm of the algebraic norm from k to p of alpha to the power of 1 over n, then this is a norm. Clearly it is multiplicative, so the only thing we have to check is the triangle inequality. So in other words, we want to check that the norm of alpha plus beta is at most the maximum of norms of alpha and beta. Now let's assume that the norm of beta is bigger than the norm of alpha, and let's normalize. So gamma is alpha over beta, and the norm of gamma is less than or equal to 1, and we have to check that the norm of 1 plus gamma is also less than or equal to 1. Okay, just by normalizing, dividing by the bigger of 2. So let's check this. And first, let's assume that gamma is primitive. That is, k is qp of gamma. This is the crucial case, then we will easily reduce to this case. So it means that 1, gamma, and so on, and gamma to the power n minus 1 form a basis of k over qp. Okay, and in this basis we write down the matrix of multiplication by gamma, whose determinant will be the norm of gamma. So A is the matrix of multiplication by gamma. So it looks like what? It takes 1 and sends it to gamma. Then it takes gamma, it sends it to gamma squared. And finally, in the last column, we will have whatever, well, I don't know, a 1n, so a and n. Okay, so the norm of gamma, by the very definition, is the p-adic norm of determinant of A to the power 1 over n. So let us consider the supremum norm with respect to the matrix coordinates. On the space of matrices over QP, and lemma, the key lemma, says that the sequence of supremum norms of all the powers of our matrix is bounded.
Well, it's
plausible because the norm of gamma is less than 1. Otherwise, certainly it would be unbounded. But let's prove this lemma. So otherwise, there is a sequence I sub j such that the norm of a to the power I j is unbounded, namely it is equal to a certain bj which is bigger than j. So it goes to infinity with this speed. Okay, and let beta j be a maximal matrix entry over a to the power j, so that the norm, p-adic norm of beta j is bj and is bigger than j. Okay, so let's renormalize. Consider renormalized sequence. B sub j is a to the power ij over beta j. Oh, sorry, it was not a to the power j, e to the power ij. Yeah. So when we divide the supremum norm of beta j is 1. So it lies in the unit sphere, and hence this sequence must have a converging subsequence. Well, I don't know how to say S1. Must have a convergent subsequence, since the sphere is compact. So we know that the determinant of bj is equal to the determinant of a to the power I sub j beta j to the negative n, right? Because we divided by the scalar our n by n matrix, which means that the determinant of bj has the p-adic norm less than the determinant of a to the power ij p-adic times j to the power negative n, because we assume that the p-adic norm of beta j is bigger than j, right? Okay, and this is equal to the norm of gamma to the power n ij, j to the power negative n, but we assume that the norm of gamma was at most 1, so this is at most j to the negative n, and so it goes to 0 as n goes to 0. Okay, now the sequence b sub j converges as n goes, b sub j, as j goes to infinity, converges to b, and hence the determinants of bj converge to the determinant of b, right? Because they converge in the supremum norm, and the determinant is continuous in the supremum norm. right? Hence we conclude that the determinant of B is equal to 0. This means that B must have non-trivial kernel. So there is a certain X in our field extension such that Bx is 0. Okay, but this is almost nonsense, and we will reduce this to absurd, because then B is just totally equal to 0, which is impossible, because B lies in the unit sphere. It cannot be totally 0. So why is B identically 0? Because B, well, we know that 1, gamma, and so on forms a basis. So then X, gamma X, and so on, gamma n minus 1 X also forms a basis. Okay, but now recall that B J's were renormalized powers of A. Now powers of A are just powers of gamma. After you multiply them by scalar, well, I want to say that powers of A, being essentially powers of gamma, commute with gamma. And after you renormalize by a scalar, they still commute with gamma. Since they commute with gamma and they kill X, they also kill gamma X and so on. Why what? Why 1, gamma, and so on is a basis? Because multiplication by X is an automorphism. In a field, any element is invertible, so multiplication by X is an automorphism. It takes a basis to a basis. So Bj commute with gamma, hence B commutes with gamma, hence B gamma to any power X is also 0. Hence B is identically 0, which is nonsense. Okay, so we proved this lemma. Lemma is proved. So now let's go on. So we know that the norm of any power of A is bounded by some constant. Okay, now the determinant of A is at most, the norm is at most the maximum of all matrix elements to the power n. Why? Because the determinant is the sum of n factorial summands. Each summand is the product of matrix elements, and we have the non-Archimedean triangle inequality. So we just have to bound any summand, but the summand is evidently bound by this, right?
Why to the power of n?
Because any. Do you remember the formula for determinant? It's like A11, A22, and so on, ANN plus similar terms. So any summand is the product of n elements, like this. Okay, and well, this is the supremum norm of A to the power n. Now, our goal, if you remember, I erased my the beginning of the proof. Our goal was to prove that the norm of 1 plus gamma is less than or equal to 1. Okay, this is what we're doing now. So we're computing the determinant of 1 plus a, right? Now 1 plus a to any power n, just by Newton formula, is 1 plus n a plus, well, n choose 2a squared plus so on plus a to the power n, capital N. Okay, hence the desired norm of 1 plus gamma to the power capital N is the determinant of 1 plus a to the power n, p norm to the power of 1 over small n. And this is at most 1 plus a to the power n, supremum norm, and this is at most the maximum of capital N choose I times a to the power I, supremum norm just by the non-Archimedean triangle inequality. And there's at most, since all the binomial coefficients are integral and have norm at most 1, you just write the maximum norm of a to the power I. And we know that this is bounded. So we know, finally, that the norm of 1 plus gamma is at most c to the power 1 over capital N, and then as capital N goes to infinity, we obtain the desired result that the norm of 1 plus gamma is at most 1. Okay, but it was only under the assumption that 1 gamma and so on, gamma to n minus 1 forms the basis. So in other words, that gamma is a primitive element. It generates our field extension k over qp. And now we reduce the general case to this particular.
I'm sorry.
Yes. Key.
Yeah, the exact equality when we're talking about the norm of the term.
Here?
No, about
Here?
But after the word now.
After the word now.
Like, I understand why it's smaller than this, but why the exact equality?
Oh, sorry. It was sorry. It was a bound. Sorry. Thank you. Okay. So in the general case, we have our field K. Inside we have QP of gamma, and we have the ground field QP. And then we already know our theorem for this layer. So we know that 1 is bigger than the norm from QP of gamma to QP of 1 plus gamma. And let's sorry, let's erase. This is certainly true, but I want to take a certain power of this inequality. Yes?
Будет норма, которую мы определяем, совпадать. Разве она не будет не зависеть от расширения?
The norm is unique, but this is not the definition. I have to take some power here. The norm, we already proved that the norm is unique.
Норма 1 плюс гамма для вот этого расширения, которое код p гамма над p, она такая же, как
No. We will have to take some power here. So I erased in order to put some power here. It's 1 over, this power is 1 over degree, QP of gamma over QP. Okay? But it doesn't matter because anyway it's 1 bigger than something to the power. If you raise it to some power, then inequality remains true. So it's the norm of from K to QP of 1 plus gamma to the power 1 over n, and this is the norm of 1 plus gamma by the very definition. Okay, so we're done. Yes. Pardon me?
So how did we use the theorem?
Well, so first of all, you know that the norm from the bigger field to the biggest to the smallest can be done in stages. You first take the norm to here, then to here. Okay. And you know that that if you take the norm from QP of gamma to QP, then already proved that this norm is at most 1. Yes. And if you take it to any power, it will still be less than 1. Okay. Take it to this power. Then because you can compute norm in stages, it's the same as here. And this is our desired norm in the field K. Maybe I should say P here.
No, but didn't you want to see that this norm is less than 1?
You want this. You want that this is less than 1, yes. Right? It is just definition. Yes. But you now replace this by that.
Is it? I mean, how do we replace? Like, why does it make sense to replace?
Because gamma lies in the intermediate field. For example,
because we know that it's unique, right?
But no. Just gamma and 1 plus gamma already lies in this intermediate field.
Okay.
So, for example, if you take the norm from, I don't know, from K to QP of the element 2, then it will be the norm from QP to QP of 2 to the power n.
So it's
just because 2 is already in the field QP. So
you mean there is a diagonal block?
Yes.
And the rest is just...
The determinant will be some power of the product of a few identical blocks. Yeah. Okay. So now let us go to some more arithmetical issues for time being, and classify all the unramified extensions. Last time we studied the Eisenstein criterion for ramified extensions, and now let's study non-ramified extensions. In fact, they are much simpler than ramified ones. Let's prove the following proposition. First, there is a unique up to an isomorphism totally unramified extension K unramified of degree F of the field QP so the degree equals F and it is obtained as QP over some primitive root of unity of degree p to the power f minus 1. P to the power f minus 1. And now the second claim is that for any extension k over qp of degree n, but now it's not totally ramified or unramified, it's just composition of ramified and unramified. So, yes?
What's the difference between totally unramified and unramified?
Yeah, maybe you can erase this. Just unramified. So if you have some mixed case, then K is the extension of this unramified. Well, maybe I should say inside there is this unramified extension of degree F, and K is obtained just by adding an element pi, where pi in OK is a uniformizer so that the norm of pi is p to the power p to the power negative 1 over e. Right. Okay. Yes.
В первой части оно единственное при фиксированной степени?
Yes, of degree f. For any degree, there is a unique up to automorphism, a non-ramified extension of degree f. So first we construct this extension, and then we prove the uniqueness while we're dealing with the second part. So we start with one, but we finish with one simultaneously with two, so to say. So let alpha bar be a generator of the multiplicative group f p to the power f multiplicative. So you know that this group is cyclic and has a generator, and we choose one. And then p bar of x, the minimal polynomial, x to the power f plus a1 bar x to the power f minus 1 plus so on plus a bar f, the minimal polynomial over the field fp. Okay, just take any lift. P of x is equal to x to the f plus a1 x to the power f minus 1 plus so on plus a f in zp of x polynomials. Then since p bar was irreducible, this lift p is a fortiori irreducible as well over zp or over qp, and we can consider the decomposition field of this polynomial. So take alpha in an algebraic closure of qp, a root of p, and consider the extension k tilde just with help of this alpha, and a tilde is the ring of integers, and inside we have m tilde, which is the maximal ideal of a tilde. Okay. Then we know that the degree of k tilde over qp is equal to f, just because it was an irreducible polynomial, and we took one root of it. Okay, and we also know that this is the degree of the residue field extension. Yes. Just because this is already irreducible modulo p, right? If it were reducible, then we could take it modulo p, and it would be reducible as well.
Yeah,
right?
Okay. Okay, it's not zero.
Yeah.
Yeah.
Can you explain why?
Yes. Where? Which degree?
Why is minimal?
Here.
Yes.
Just because you know that it is a generator of this field, right? Because it generates the multiplicative group, so a fortiori it generates the whole field, but the field has degree f, so the polynomial must have degree f, right? Just by when you're in doubt, you just always say by Galois theory. And why are you in doubt?
Like
You-
C over R.
Huh?
C over R. If we take
Yeah.
the degrees to
Yeah. So, what could be wrong? The degree is what? Less than f or more than f? What is? What do you suspect could be wrong?
I don't understand why
Yes.
it will be less than F. For example.
Because it generates the whole field.
Yes.
But if your polynomial had degree less than f, then the corresponding field extension would have degree less than f. You know, it generates the whole field. So it must be at least f.
And why it could not be more than F?
Because it's an irreducible polynomial. Okay?
Yes, but what about again, so if we take this model of P,
Yes.
so why could it be something that reduces to like 1, let's say, like trivial thing? Like you have, let's say model of P.
So this f must be f prime plus f second. And you have two polynomials of degrees like this that multiply to p. Right?
Yeah.
With integral coefficients, say by, how it is called, Gauss lemma, whatever, with content. So I mean that if it's decomposable over QP, it must be decomposable over ZP. But then the decomposition over ZP, just by reducing modulo P, gives rise to decomposition over FP, which is, but it was supposed to be irreducible. Okay.
Можете повторить,
Yes.
как мы получили, что косвенный на ТУП это F?
Just because the k tilde is obtained by adjoining alpha. Alpha is the root of polynomial of degree f. So this degree must be f. Right? Okay, and this is the same as the residue field extension degree. So k tilde is unramified.
Why is it the degree of extension?
Pardon me?
Why it is the degree of extension K over P?
Here?
Yes.
Because because we know that at the level of residue field, you get the this extension.
Small k is the residue field, right?
Yeah.
So
So you
try to get FPF on the residue.
just because we took a root, this root is a integral, right? And we can reduce it modulo p, but over p this will be the root of this equation, and it will have degree f. So it could have a smaller degree. This could be something smaller, but we know that it's f. So it's totally unramified. Okay, so we constructed one particular unramified extension. We need to prove that any other one is isomorphic to it. We will do this momentarily. So we will prove the uniqueness in 5 minutes. Okay. Now let's go to the second part. And assume that we have extension of degree n, and n is the product of ramification degree and unramified index. And again, we have the ring of integers and the maximal ideal. And the quotient is f p to the power f, just by definition, because the non-ramified degree is f. Fine. And again, in here we take any generator, just as we did. Of the multiplicative group. Okay, and take any lift alpha naught in A of alpha bar, and choose any uniformizer pi in the maximal ideal, the generator of the maximal ideal, such that the order of pi is 1 over e. Okay. Then let us prove another lemma, namely that this. Yes.
I have a question.
Yes.
Why did we actually write that this n-ramified is qp over this the root of degree pf minus 1? Since we say that this alpha is a generator of the multiplicative.
Yes.
But it has, I think.
So you mean that I didn't yet prove it? Yeah. That's what you mean. You are absolutely right. I didn't yet prove it. I'm going to prove it in 5 minutes. I didn't finish the proof of 1 yet. We will finish it soon. So the lemma is that there exists alpha. We can correct our choice of alpha naught. So there exists alpha that is like alpha naught modulo pi. But now alpha to the power pf minus 1 is just 1. Proof. In fact, we already had a proof. This is just Hansel lemma. But it was a long time ago, so let's go over it again. So we'll do this by consecutive approximations, successive approximations. So first of all, I write that alpha will be equal to alpha naught plus alpha 1 pi modulo pi squared. But I want this equation to be solved. So what do I see? That 0 must be equal to alpha 0 plus alpha 1 pi to the power p to the f minus 1 minus 1. And we know that this is just alpha 0 to the power pf minus 1 minus 1 plus p to the f minus 1 times alpha 1. pi alpha 0 to the power p to the f minus 2. And this is just alpha 0 to the power p to the f minus 1 minus 1 minus alpha 1 pi alpha 0 to the power p f minus 2 modulo pi squared. Okay, but we know that alpha 0 to the power p to the f minus 1 is 1 modulo pi squared, modulo pi. And hence we can solve the equation, linear equation for alpha 1, namely that alpha 1 will be alpha 0 to the p to the f minus 1 minus 1 minus 1 divided by pi times alpha 0 to the power pf minus 2. Okay, modulo pi. So we've found the next correcting term, and we can continue like this, like in the proof of Hensel lemma, to get alpha equals alpha 0 plus alpha 1 pi plus alpha 2 pi squared plus so on. The infinite series, but convergent. Well, maybe I don't want to erase this.
Excuse me.
Yes.
А вот альфа, которую мы строим,
Yes.
она в К, да?
Certainly, yes, it is in K because because everything here is in K. It will be the convergent series with coefficients in K, so it will converge to something in K. Right? Because all the terms are in K and it converges. Okay. So now alpha. So alpha is the solution of this equation, but not a random solution like 1, for example. Yes.
Now the case complete.
Because it is a finite dimensional vector space over QP. Yeah. So alpha is a solution of this, a root of unity, but not a random one, but lift of the generator of the finite field multiplicative group, and in the finite field this is the generator. So this alpha also must be the primitive root of unity. So only its p to the f minus first power will be 1, and everything else will be not 1, so they will be all distinct. Alpha squared, and so on. Alpha to the pf minus 1 equals 1 are all distinct. And alpha is a primitive root of unity of this degree, p to the f minus first root of unity. Okay. So it implies that the degree of QP of alpha extension over QP is at least f. Okay. now apply this argument to the field K equal to K tilde. So we started with construction of K tilde, which I erased already. But we did construct some particular unramified extension, okay, of degree F. Right, I promised to prove the uniqueness. Now we return to this question for unramified extension, right? And so we argued something for general extension, and now we'll apply it to the particular case of this one particular example of unramified extension, right? So what do we see? We see that F equals the degree of K tilde over QP, which is at least the degree of QP of alpha over QP, which is equal to F, which is at least F. So here we must have an equality. So K tilde must be equal to QP of alpha. And that's what I promised to prove. Right? That K tilde is obtained by adjoining the PF minus 1 root of unity. And now I did what I promised to do. Now it remains to prove this part, that K is obtained from this unique unramified sub-extension just by adjoining a uniformizer. Yes.
Вот когда мы доказывали лемму, нам нужно было на альфа-иты условия какие-то, что они альфа-иты целые или не нужны такие условия? Чтобы сходимость была.
Yes, certainly. We want alphas to be integral, just integral, nothing else.
Почему такое получается?
Why is it integral? Well, what's the question? Why alpha 1 is integral? Because it is divisible. Just we proved this. We proved this divisibility, so we're allowed to divide.
А норма альфа 0 это 1, да?
Yes, just because alpha naught is a root of unity. It's not zero in the residue field.
Yeah.
Right? So it's invertible. So I erase this. But we are almost done. And well, it turns out that the unramified extensions are the simplest extensions. Like, for example, if you study the Galois group of the p-adic field, then it has some quotient which corresponds to the maximal unramified sub-extension. So you'll have QP bar, then inside you will have QP unramified, inside you will have QP. And it means that there is an exact sequence of Galois groups, 1, 2, Pardon me? QP unramified?
Yes.
Well, I just proved this part, right? I proved that any extension whatsoever has canonical, unique, maximal unramified subextension.
How we proved uniqueness?
Just I constructed the.
Yes, but suppose we have two roots and.
But they are this. They generate the same extension. Each one is the certain power of the other one, so it generates the same extension. So when they prove that it's canonically, uniquely defined,
Yes.
the maximal unramified subextension, it's unique. And in particular, if you go to bigger and bigger extensions, well, you get an algebraic closure here, but inside you get the unramified closure like here. And at the level of Galois groups, you have, I don't know, maybe gamma Galois group QP bar over QP. And then in the quotient you get the Galois group here, which is the same as the Galois group of an algebraic closure of finite field over finite field, so which we know is Z hat. Though this one is it's the unit element, but from this point of view it's rather zero. Sorry for this. Okay, and Z hat is as you go to infinite extension, the Galois group is the projective limit of finite Galois groups. So it's a profinite group. It's a profinite completion of Z hat. Maybe FZ. Pardon me? Gamma is the kernel. Is the kernel, the ramification part of the Galois group. And then it is known that this gamma in turn has filtration. So 1 goes to gamma p, goes to gamma, goes to, well, how should I say this? Well, maybe let me write it down. Z hat is the product of over all primes ZL. Yeah, just by the Chinese remainder theorem. Maybe we in a sense we discussed this, but well, anyway, that's true. And here you get the product over all L not equal to P, ZL but of 1. This of 1, there's the Tate twist, meaning they're, well, abstractly they're isomorphic to just ZL. But the Frobenius generator in here acts on gamma, and in particular this quotient, by conjugations. And this action is like the actions on the roots of unity. So it takes them to some power. It's not non-trivial action. And this is, so this part, well, it's called gamma tamely ramified, gamma tame. So gamma tame is the projective limit of roots of unity of degree prime to P. Okay. And then gamma P is a pro P group. And well, this is very explicitly known, just generated by Frobenius. This is also very explicitly known, but this is not explicitly known, and this is the whole point of p-adic arithmetics.
So what's generated by Frobenius?
This z hat is the Galois group of the finite field. So
Если вот это Z-крышка, это расширение, это группа была чего?
so the Galois group of QP unramified over QP, as I just explained, is canonically the same as the Galois group of FP bar over FP. And this is canonically Z hat just generated by Frobenius. So this quotient is just the Galois group of the unramified extension, the same as finite field algebraic closure, and it's the hat generated by Frobenius.
Потому что у нас такие же, оно получается таких пределов с добавлением таких же корней.
Yeah, just we I don't know. Just if you go to the residue field, then the Galois group is absolutely the same. We proved that it's unique up to automorphism. The automorphism group is the same, just the Galois group, automorphism group, is the same as the Galois group of the finite field. You just take any power of this generator, which makes it still primitive root.
А это правда любого не unramified расширения?
Yes, for any unramified extension, yes. The unramified extensions are just the same as for the residue field. So in this sense, their theory is very elementary. And then there is this ramified part, which is much more subtle, but still it has the part which has degree prime to p, and this is relatively well understood. But then it has another part, which is absolutely mysterious, of degree. So like when you take QP, and then you join the root of p of degree p, for example. This will be a wildly ramified extension. It's totally ramified, and the degree of ramification is some power of p. And this is somehow the main problem of arithmetics of p-adic numbers. Yes?
What do you mean by pro-p group? Gamma p?
That's the projective limit of finite groups, and all these finite groups have order p to some power. The orders here are prime to p, but the orders here are powers of p. Okay. And this is the most mysterious part of the Galois theory of QP. And like the famous Langlands program is how to understand representations of this pro-p part. Okay, so while I was erasing, I started this mumbling, but I still had to prove the last part of the theory. So let me prove the last part of the theory. Yes?
Is it true that unramified extension is always normal?
Yes, absolutely. Yes. You see that the Galois group is the cyclic group of order f. The Galois group of the... Pardon me?
Arbitrary unramified extension.
Yes. It's just the same as for the residue finite field. And you know that for a finite field, any extension is normal. The theory of unramified extensions is identical to the theory of extensions of the residue field. Everything is just the same. The Galois group is the same, everything is the same.
Это вообще, в принципе, не обязательно купе, а просто...
But then you have to explain what do you mean by unramified. For example, the field of rational numbers, Q, has no unramified extensions whatsoever. It's a deep theorem due to Kummer. But bigger arithmetical fields do have unramified extensions. But then the maximal unramified extension has some only finite degree. If you start from some field of algebraic numbers, then it does have some unramified extension. I mean, the induced extensions of all the local fields, when you complete with respect to any local norm, will be unramified in this sense. And that's just the definition of what I mean by unramified extension of a global field, like Q. It means that the induced extension of any QP is unramified. When I say unramified extension of Q, what do I mean by this? I mean that if you complete with respect to P norm, you get an extension of QP, and this is unramified. And then the deep theorem by Kuma says that there are no such extensions, just Q itself. Any degree bigger than 1 extension is necessarily ramified somewhere at some prime. But if you take some bigger algebraic number field, then there are everywhere unramified extensions, but there is the maximal one. But then this one in turn may have its own unramified extension, non-trivial, and then so on and so on and so on. So there's an infinite tower of. Pardon me?
Infinite tower of unramified.
Yes. Mm-hmm. Okay. So what do I still have to prove? I still have to prove that any extension K is obtained from its canonical maximal unramified subextension just by adding the a uniformizer. And this is very straightforward. So let E of x, E for Eisenstein, be the minimal polynomial over some uniformizer pi over this k tilde equals the maximal unramified subextension. And let pi sub I be all the elements conjugate to pi over k tilde. Okay, so that E of x is the product of x minus pi I. Okay, and say D is the degree of E of x. Pardon me?
So why the polynomial is completely reducible into linear fashion? Because like this normal.
K tilde is normal, but K itself not necessarily, this one is not necessarily normal, so what do I want to say? Maybe I don't insist that those pi's lie in pi i's lie in K. Okay, let them lie in K bar, wherever. Okay. So D is the degree of this polynomial, and let C be the constant term of E of x. Okay, then the p order of C is equal to D times the p order of pi, because all the conjugates have the same p order, right? And this is equal to D over E, right? Because pi was a uniformizer, and its p order was 1 over E. Fine. Now we know that E times F is n, is the degree of K over QP. And again, we have this two-step filtration, so it's the product of K over K tilde times K tilde over QP. So it equals to K over K tilde times F, which implies that D is at most E. Right? The degree of this polynomial is at most E, but we know that the p order of the constant term is a usual p-adic number, p-adic integer. So the p order must be integral. Okay, and this can only happen if D equals E. And then the p order of C must be exactly 1.
Why C is p-adic integer?
Just because this is the polynomial over. Well, maybe I shouldn't. The norms of an ramified extension are all p to the power z, right? So and this is the minimal polynomial over the ramified, so its norm is integral. The p order is integral. Okay, so we are done, because this means that p of x is an Eisenstein polynomial. And K is K unramified of pi. That's it. Thank you. Yes. Yes.
Правда, что вот если носить какое-то расширение, то в нем есть прям максимальное по включению неразветвленное подрасширение?
Yes. That's the whole point.
Просто если... А мы доказывали сейчас это.
Yes, that's what we proved in the second part. That such an extension is unique and any extension has the maximal unramified subextension. Well, we could in principle have like what? Like 1k inside 1k tilde and another k tilde tilde. This could happen, but we proved that they are the same. Just because there is unique such extension.
Можете повторить план? Как мы это получили?
Because we identified both of them with this. We constructed an element alpha by Hansel lemma inside, which is the exact solution of this equation.
Inside both of them.
Inside K. Inside K we constructed.
Okay.
Then we applied this to the case when K is K tilde, and proved that K tilde is generated by a root of unity.
А зачем нам нужен был многочлен Ядекс какой-то?
Then I proved the second part. The second part is that the whole extension, not necessarily unramified, is obtained from its maximally unramified subextension just by adjoining a uniformizer.
Как мы это получили примерно?
This last part is still on the blackboard. So we did adjoin uniformizer, and then we proved that its minimal polynomial must be an Eisenstein polynomial irreducible of degree E.
I'm sorry.
Yes.
Why did we get the D's less than D here?
Just because
It has something to do
the degree of this polynomial is at most degree of extension. The degree of minimal polynomial is at most the degree of extension.
А что мы все-таки сделали с тем, что расширение обязательно нормальное?
Nothing. We didn't use anything at all. We just still it can be written this way, where pi i's are elements not necessarily in K, in some ambient bigger extension. Yeah. But this was probably one of the most algebraic classes. Then we'll move on to analysis, p-adic analysis.
А можете, пожалуйста,
Yes.
в какой вообще общности есть такие понятия, как неразветвленное расширение? Просто вот я раньше слышал, что если у нас есть декиндова область,
Yes.
то для ну там локальные кольца это кольца нормирования дискретного.
Yes.
Сейчас, ну вот просто вы как есть вот в декиндовой области есть какие-то локальные поля, и вот иногда unramified это вот случай, когда говорится про локальные поля, иногда вот когда про декиндовую область. Как это все соотносится друг к другу?
So it's the theory of the rings with a unique maximal ideal, and moreover principal maximal ideal. So Dedekind domain. So we are using that there is that any ideal is any ideal whatever I is pi to some power for uniformizer pi. And then for these rings and their quotient fields, there is a notion of ramification and so on.
Это кольца дискретного нормирования.
Yes. Discrete fluctuation rings, DVRs.
Почему тут локальные поля? Что такое локальные?
Because any local field is the fraction field of a DVR. The ring of integers, well, except for complex and real numbers, non-Archimedean local fields, they are always the fraction fields of DVRs. And then for any global field, there is a notion of ramification at a point.
А как соотносится глобальный поля и Дедекиндова область?
And what is Dedekind domain by definition?
Это одномерная Нётерова область, замкнутая, но это равносильно тому, что каждое локальное кольцо – это кольцо дискретного нормирования.
Okay, then the global fields are again the fraction fields of Dedekind domains. And they are either the fields of algebraic numbers or finite extensions of Q, or they are fields of rational functions on a curve over a finite field.
Thank you.
Welcome.
Sir, can you
Yes.
kindly tell me what gamma p is? I mean, I couldn't understand that.
Gamma p was the wild ramification Galois group. So the Galois group of QP bar over QP had this unramified quotient z hat, and the kernel was by definition this gamma. Okay, yeah. And then this gamma had some quotient gamma tame, and the subgroup gamma wild, and this was pro prime to p, and this was pro p. So this is projective limit of groups whose orders are prime to p, and this projective limit of groups whose order is p to some power. So the structure of this group is a big mystery and the heart of p-adic arithmetics. Yes?
Откуда у нас появился морфизм гамма в гамма-т?
Well, just definition. This is a profinite group, and it has the maximal quotient that is pro prime to p. Just by definition. So at any finite level, if you have a finite extension, then first of all it has non-ramified part, then you're only interested in the ramified part. The ramified part at finite level has some maximal quotient which is prime to p. It is called tame, just by definition, nothing
Хорошо, а как
deep.
получилось, что гамма-т это произведение z?
Well, it's some question of, you have to compute it, but it's an easy computation. Well, it's a question. Maybe I can give it as a home assignment, but it's not hard. The hard part is to say something about the wild part. Thank you.